Okay, we're back. Cool. So continuing, that was note set 12. Note set 13 covered two very important topics. The first being Fourier series, second being Laplace transforms. Those are the two big things that are in this note set. When we talk about Fourier series, we first need to understand the concept of periodicity, whether or not a function is periodic. And the way that we did this is that we looked at a function that we wrote as the sum of sine waves. Oops, what is going on? Hold on a second. That was weird. You looked at this thing, which is the sum of sine waves. Wait, why is... Hold on a second. I think my team stopped sharing for the recording. Hold on. It did. You guys like, oh, I got to come to class now. Give me a second. Okay, now we're up. Cool. So the idea with periodicity is that we want to look at the frequencies of both of these different functions. I wrote it as 2 pi times 3. Why do you think I wrote it like that as an introduction? It's 2 pi f, right? This is sine of omega t, where omega is 2 pi f. So what is f for this first sine wave? 3. What is that for this one? 4. Now the test for periodicity is to check that the ratio of these frequencies is a rational number. Is a rational number, not irrational, a rational number. So f1 over f2 is 3 over 4. That's rational. If I have multiple frequencies, you had one in your homework with 3, it's just the combination of all of them. f1 to f2, f1 to f3, f2 to f3. If all of them are rational, then you're good. That makes sense. Then it's periodic. So I showed you here these two graphs from class. The red one is sine of 2 pi 3t. So if you were to look at this curve, we see that I'm highlighting it in red right now. It repeats after 3 cycles. That makes sense. That's a frequency of 3 hertz, 3 cycles per second. So in a second, you will see that we end up with 3 cycles. If you look at the blue, which has a frequency of 4 hertz, this will have 4 cycles in that same amount of time. You see there's 4 sine waves there, right? That's 4 sine waves. Now, if you look at the two together, they are both doing their own thing. But what we see is that eventually they both start over at the same time at 1 second. There is no other time where they overlap perfectly and they share the same force value. Remember, force is the y-axis in this example. Besides at 0, the next time where they're equivalent, where they overlap perfectly, is here. Do we buy that? Do you see that? Anybody not see that? So the reason that that's important is that if you were to add these together, which is what that problem was, sine of 2 pi 3t plus sine of 2 pi 4t, if you added them together, you'll get this weird thing that will repeat after 1 second. You can see that these two things here are exactly the same. They just happen to repeat after a second, because that is when the two sine waves start over in unison. Is that okay, Audrey? Okay. So for this example here, I give you 3 in the square root of 5. If you make a fraction out of those frequencies, that is irrational. That is not valid. This is not periodic. Yes, that was like you had one in your homework. That was like the square root of 125 and the square root of 5. Because if this was the square root of 125 divided by the square root of 5, that ratio is the square root of 25, which is 5. That makes sense? So that's okay. That is rational. The square roots can end up being rational depending on the values inside. So if it is periodic, the way that we determine what frequency it oscillates at, so for example, we know that this one here repeats itself every second. What's the period of this motion? One cycle. It takes a second for one cycle to happen. What's the frequency? It's also 1. So we see that the period is 1 second. And we see that the frequency will be 1 hertz, the reciprocals. Now we called this a very special name. What was this called, this frequency? It's the fundamental frequency because we're having so much fun. If you look, I give these subscripts capital T, basically associating it to the period of the overall motion. Omega T is 2 pi times that frequency, right? That's the angular frequency, the fundamental frequency in radians per second. The question is, how do we determine that based off of our individual sine waves? So what we do is we look at the periods, which again are the reciprocals of the frequencies in hertz. So the first function will repeat every 1/3 of a second. The second function repeats every 1/4 of a second. What we want to do is to see when they match. When they match. So what we did was say, okay, after 1/3 of a second, we have 1 period. Oops, let me write this better. After 1/3 of a second, we have 1 period. After 2/3 of a second, we've had 2 periods of this sine of 2 pi 3t specifically. After 3/3 of a second, we've had 3 periods. Is that okay? Okay. For the 1/4, we see that we had 1/4 of time passed. That's 1 period of this motion. 2/4 would be 2 periods. 3/4 would be 3 periods. And then 4/4 is 4 periods. And we want to see when they're both equal to the same value, because that'll dictate when the overall thing will start over. And in this example, we see that it occurs when both of these periods are equal to 1. If we come back to this graph, let's just look at the blue one, or sorry, the red one, which is the 2 pi of 3t. So if you look, I'm trying to, maybe I'll do it in black. That is 1 period of motion. This is at 1/3 seconds. We've completed 1 period. If we do another period, we see that now we're at 2/3. We do one more period. That's 3/3. 3 periods have passed for this first guy. Is that okay? If you do the same thing with the other, you'll see that 1 period has passed. I'll go up. This is at 1/4 of a second. Another period is passed at 1/2 a second. We can see it aligns perfectly with a 1/2. That's 2/4. Another period is at 3/4. And then another period is at 4/4 or 1. We see when we're counting the multiples, we want to see when the two multiples are matched, because that'll imply that they're both starting over at that point in time. Does that make sense? Doubts about that? So that is why we do this whole counting periods thing and see when they match, because that's what it's going to look like on the graph. So from this, we can say that the period of the overall motion will be 1 second. 3 over 3, 4 over 4, that's 1 second. That's when they both match, which means the fundamental frequency is 1 hertz. We got that before. The fundamental frequency in radians per second is what? 2 pi. So now we know the fundamental frequency of the motion. Is that okay? Why that is so important is that if you want to decompose a periodic function into a Fourier series, we need to know what that fundamental frequency is. We can do that by looking at the graph and seeing when does it repeat itself, and then say, okay, that's the period. We can find what omega is. That omega is important because it is used inside of the Fourier series. To summarize this, what we are trying to do is to break down a periodic function into an infinite sum of sine and cosine waves at different frequencies, where each of those individual sine and cosine waves can have different amplitudes. The amplitudes are the A sub n and the B sub n. Those are what we call the Fourier coefficients. Those are the amplitudes of the sine waves. So these things are the Fourier coefficients, which are the same as the amplitudes of the sine waves. Do we buy that? Do we believe that? Okay. What's A naught? That's the mean of the function. This basically will shift our sum of sine waves up or down depending on what the mean of the function is. So we look through these terms, like for example, here is the same function plotted on the same graph. The only difference is I shifted this function up by 5. That's what A naught is. It's the mean of the data. So if I were to take the mean of this graph and I were to integrate this weird thing, whatever, we will see that the average ends up being perfectly 5. So we have to shift that up to make sure we get the right response. So by definition, the average of a function based on an integral is to sum up all of the integration terms and divide by the number of times. And that's like an average, sum up things, divide by the number of things, except in terms of time. The period, that's the period of the motion. Because remember, this is a periodic signal where it repeats itself every X amount of seconds. So we want to integrate across that period. Make sense? That would be T for the previous example I showed you. That's correct. But again, it depends a lot on the functions. But for that example, it's 1. So this next term is the one that gives people the more difficult. The more difficulty is determining what A sub n and B sub n are. So if you were to go, first off, you need to know what omega t is for all of these things. You can do that based on what we just talked about. That's 2 pi over the period of the motion. Again, this is 2 pi times f t, and then reciprocals. So 2 pi over the period will be the fundamental frequency. So here's an example where I give you this force. I could have given you the original weird function that describes it. What's going on? I see so many people giggling. Really? Okay. Something happening, Emery, Connor? I don't know if there's any that look weird, something happening right now. Okay. So if I'm going to take a periodic force to decompose it into these 3 sine waves, what we see is that these guys are the amplitudes What letters do those correspond to? A sub n or B sub n? B sub n, because they're multiplied by sine. A sub n is multiplied by cosine. And this F1, F2, and F3, how are they related to each other? Thank you. They are frequencies. How are they related to each other more specifically for Fourier series? Let's scroll back up to the definition. No, we already know it's periodic. What'd you say? Not ratios of each other. We see that we have n times omega t. They're multiples of each other. So for example, if I do sine of 2 pi times 2t plus sine of 2 pi times 4t plus sine of 2 pi times 6t, this is F1, that's F2, and that's F3. Do you see that they are multiples of each other? N times F1, let's say n is 1, n times F, or F2 is n times F1. So that'd be twice the first frequency, 3 times the first frequency, and so on. We're looking at multiples of that fundamental frequency. That's what this n omega t means. They're multiples of it. Do we see that? Doubts about this? Jacob, okay? So in this example here, F1 is the thing, F2 is twice F1, F3 is 3 times F1. They're multiples of each other. Is that okay? So in this example, I give you this gross sine wave, which I told you in this note set that it's the sum of these 3 individual sine waves. If you did the Fourier series on this, you will get something that looks like this. How do you read this graph? What is this graph showing us? Let's look at the axes. The first one's frequency. The y-axis is amplitude of the Fourier coefficient. It's showing us the force, right? We said before that f of t is a1 sine of 2 pi f1t, a2 sine of 2 pi f2t. Huh? They're kind of included in that, right? So for this example, I wrote it like this. So for this specific example, they won't actually end up being 1 times or 2 times. So what frequencies are present inside of this sine wave, or this periodic function? 1, 5, and 8 are all present. Do we see that? 1 has a peak, 5 has a peak, 8 has a peak, and 0 everywhere else. So this might be something like sine of 2 pi times 1t from this, plus sine of 2 pi times 5t from this, plus sine of 2 pi times 8t from that. Do we see that? Makes sense now, Michael? The ends are kind of buried in it. We'll talk about that in a second. Yeah. That's correct. Correct. So the amplitudes are based on the height of these graphs. The last one would be 6. And that's exactly how I made that MATLAB figure. I added these 3 things up together. We didn't talk about how to find the Fourier series in MATLAB. But in general, you can take that data and it'll find for you the values of those coefficients. So let's say that this is the fundamental. This guy is FT. What do you think this is? in regards to n? What n value is that? Well, for that, it's 1. What about for the next one? Like the multiple. If f of t is 1, what multiple is 5? Yeah, it's 5. N is 5, right? For this case. And then this one would be 8. Those are the n values. So if you correspond this to the Fourier coefficients, this would be B1, this would be B5, and this would be B8. Do you see that chart? Take a second to digest that. Remember, it's a sum of signs. In this case, there are no cosines. I didn't give you a cosine graph. Yeah.
So there is like a 2 and 7 prohibition.
That's correct. It does exist technically, but B2's contribution doesn't exist. So it's 0. B3 is 0. B4 is 0. B5 is not 0. That's equal to 4. B6, B7 are 0. B8 is equal to 6. Those are the 3 frequencies that are present in the overall function. Are we okay? Okay. So I gave you the equations for how you would actually find A sub n and B sub n. You've done this in your homework. You've done this on your quiz. It takes a while, but what helps us simplify so it doesn't take as long? The idea of even and odd functions. So cosine, even or odd? Even. How do we know that? Huh? That's the reason why it's even. It's symmetric about the y-axis. So that's symmetric about the y-axis. That's cosine. The dumb way of remembering it is by the number of syllables. That's honestly what I have in my head when I think about this. Cosine is 2 syllables, as well as the word even. Cosine, even. Sine is odd. Sine, odd. Amazing. Dumb thing to remember. If you get confused and you're like, oh, I don't remember which is which, just remember the number of syllables. It's really nice and convenient and easy. If you clap during the exam, I'm going to assume it's for me, and that's going to boost my ego, so don't. Peter.
Is that in the real world?
What, this idea of integration? Oh, I do that at my job all the time. I'm like, and a big conga line bursts out. You know, that's what we do at work. So, that's me. So, the reason that is useful is that if you know that sine or cosine, or even or odd, is that if your function itself is even or odd, that will cause one of these integrals to go to 0, which is really convenient. So let's say that this is even. Which one of these is 0? The n is always 0. Even times odd is odd. Well, this is actually not the correct form. What would be the correct form? It's 2 over t. What do the bounds have to be? Yeah, negative something to positive something. They have to be equivalent about the integration. Because again, if you were to integrate an odd function is something like y over x, you have to go from like negative a to a so that this negative area cancels with that positive area. So you always have to change the bounds to be symmetric about the y-axis. A lot of times I'll give you problems that are like from negative pi to pi, something nice and convenient, right? So if you have even times odd, that'll give us ultimately an odd function, which will be 0. How do we simplify the top one? Instead of going from 0 to t, I'll go from negative pi to pi. That's correct. No, it depends on the f of t, right? And even. Yeah. The way I explained it in class originally was wrong, but I'll say it correctly here. The way I'll think about this is like the multiplication of positive and negative numbers. So if I do positive times positive, that's positive. This is the same as like even times even is even. If I do negative times negative, that is positive. Odd times odd is even. Then if I were to give opposite signs, that would be negative. That's the same as even times odd is odd. Okay? That makes sense what I just said? Matt. That's based on the graph. So if I give you a graph that looks something like, how do I want to draw this? Like one example I gave was this. I think we had the square wave example. The question is this odd or even? Is this symmetric about the y-axis? Is it symmetric about the origin? Odd means it's about the origin. So we would, if we were to flip this about the origin, it would end up being mirrored. So that is considered an odd function. An example of an even function would be something like y is equal to x squared. That is even, because we see it reflects over the y-axis. A little trick too is that if you have, let's say, a polynomial, if the exponent is even, like x squared, that'll be an even function. If it's x cubed, it's odd. So you'd have to look at the graph and figure out if that's the case. Is that all right? If you are integrating from negative a to a, integrating an odd function would be 0. That's correct, Gael. Yes. The definition is 2 over t. If I change the bound from 0 to t, from negative pi to pi, this is just a definition in general. It's going to be across a period. If the period happens to occur between negative pi and pi, we would just replace those bounds. You don't need to do any sort of manipulation because you changed the bound. That might have been for a very specific example. So in this example, the reason it was 1 over pi is because the period, if you look at this period was 2 pi specifically. So then you see that the 2's ended up canceling, which is why it ended up being 1 over pi. Is that where that came from? Is that where this question came from? Okay, perfect. But yeah, it's still the same equation, just reduced. So we did an example here. This is an odd function. We can see that because it's symmetric about the y-axis. So we see that I'm going to look at this and this. And then we see that the motion repeats itself. So that is our periodic function. And our goal is to determine what the Fourier series is. Looking at this, what's the period of the motion? Yeah, it goes from negative pi to pi. This distance here is 2 pi, right? That's 2 pi. Our fundamental frequency, F, is what? Well, an omega be 1. What is it in hertz? Tristan, what are you going to say? 1 over 2 pi. The reciprocal of this, right? Period and frequency are reciprocals. Now, omega t will be 2 pi times that. That ends up being 1, right? Also, is that what you were saying? That's 1. Our fundamental frequency is 1 radians per second. So I go through this math here. F of t, we said, was odd. What's cosine? Even. Even. So a sub n should end up being 0. I actually went through this integration here, but we end up getting 0. If you don't remember the rules, you could integrate. It'll just take you more time. Now, let's say we have this integral here. F of t, we said, was odd. What sign? Odd. So I say even. Don't do that. So what's the product? Odd times odd is even. So if I have 1 over pi, the integral from negative pi to pi of an even function, how can I simplify this to make my integration easier? Yeah, if you think about a graph that's even, let's say I give you the quadratic again, this is even. This area and that area are equal to each other because it's even. So what I can do instead is just integrate from 0 to pi and double it. So this will be the same as 2 over pi, the integral from 0 to pi of the even function. That saves you a lot of time. Because instead of doing 2 integrals, 2 separate ones, you just have to do one, which is a lot simpler. So using these even and odd tricks will help you in terms of saving time and also saving mistakes. If you have to integrate a second function, there's more room for error. Do we buy that? Doubts, concerns, fears? Yes. I don't think I used this here. I just did all the algebra. If you go through this, you end up getting this expression for b sub n. This is very specific for this example. Very specific for this example. So what does this mean? B sub 1, that's going to be the coefficient of our first sine wave. Again, let's think about this. B sub n, our Fourier series is a naught plus the summation of an cosine n omega t plus bn sine omega t. That's the definition. In this problem specifically, what was the mean? It was the square wave. It was 0. And we just found that a sub n was 0, which means that all this goes away. We were just left with this b sub n term here. Do we see that? Do we see that? So if I were to write this out, this would be b1 sine of 1 omega tt plus b2 sine of 2 omega tt plus so on. b3 sine of 3 omega tt, 4 sine of 4 omega t, etc. We're looking at multiples of that fundamental and seeing their presence. Is that okay? So this is the general expression for b. So if I wanted to find b1, I would plug in 1 for n. What's cosine of pi? -1. 1 minus -1 is 2. That first coefficient is 4k over pi. So that will go right here. That is the amplitude of that sine wave that is present inside of that periodic function. You would repeat, if you did this for b2, get 2k over 2 pi 1 minus cosine of 2 pi. What's cosine of 2 pi? 1, which ends up causing 1 minus 1 is 0. We get B2 is 0, which means that this frequency, 2 omega t, does not exist inside of our periodic function. It doesn't exist inside the square wave. Because that coefficient is 0, that doesn't exist. Again, we're looking for the presence of what sine waves are in our periodic function. So by showing that B1 is non-zero, that means that the fundamental is present. By showing that B2 is 0, that means that double the fundamental is not present. And you can repeat this process. I even generalize it here to say that it's always going to be 4k over n pi for odd n. We got 4k over pi for B1, we get 4k over 3 pi for B3, and so on. Confusion. The reason that this is important, I think I talk about it next. Talk about odd and even already, we did that. Is that if I give you some force f of t, that is this square wave. It's causing this mass to move. This might be difficult to deal with in regards to finding the response of x of t. You could do convolution and stuff. You could do that. We've talked about that. Or you can represent it as the series of sines and cosines, which we know how to solve. Using superposition, we can say this system is equal to sine of, n omega tt for some n, find x of 1 of t. Repeat it for the next sine wave, find x2 of t. Total response, add them together. So basically, we're taking this complicated thing and we're writing mx double dot plus cx dot plus kx is equal to, let's say, we'll base it on the square wave, just the b1 sine of 1 omega t plus b3 sine of 3 times that. And you would do it from 1 to infinity. Let's just pretend we use this to approximate the square wave. You can now solve this differential equation twice. Once with this as the forcing function only. So basically, this wouldn't exist. And then once with the other forcing function only. You find x1 of t, x2 of t, add together. Now you have the response due to both of them. That's the motivation behind this. You can take any arbitrary force and break it into sines and cosines, which we know how to do from the previous note sets. That makes sense? That's why this is useful. Questions about that? Okay. Laplace transform. The whole benefit of this was what? You don't need to do convolution, because I know that many people typically don't like convolution. It's all right. But if you prefer to do something that involves Laplace transforms, what we learned I'll come back to this in a second, is that if you wanted to convolve two things together, which will give us x of t, you can say that x of s is the product of those two Laplace transforms. Yes. Yes. I might say to you, use whatever method you want, or I'll tell you specifically, use convolution, use Laplace transforms or something, right? I'll be specific. And if I will tell you, you can use whatever you want, I'll write that in words, you can choose, or I'll tell you specifically, use one of the two. So what this is saying is that the Laplace transform of x of t is equal to x of s. This is f convolved with h. That is the same as f of s times h of s, which again is very nice and convenient. We can go ahead and avoid the convolution stuff by taking Fourier transforms. So in this example, I give you the forcing function, I give you h of t. We can use the table to figure out what the Laplace of this is and what the Laplace of this is. and I did it with convolution to show you, but if you were to go and look at the Laplace of this and the Laplace of this, the forcing function and the impulse response, you can multiply them together to give you what x of s is. Take the inverse Laplace of that, again using the tables, and you find out what x of t is. Done. You have a problem in your homework that's due tomorrow that's based on this. That problem's a little bit harder than what you would expect on an exam because of the fact you have to use what? And make you use partial fraction decomposition on the homework. You won't have to do that on your exam. No partial fractions. This isn't a Calc 2 class. So the other reason Laplace transforms are important is that you can solve differential equations with them. You can take the Laplace transform of both sides of your differential equation and then end up solving for what x of s is. Again, we want x of t, so we take the inverse Laplace to get x of t using a table, and you end up getting the thing that you would expect for that differential equation. That makes sense. That's the idea. So I give you an example here. What does the thing on the right mean physically? Yep, more specific. Yeah, what's that mean specifically for physics? It's delayed. We don't hit it until pi seconds. So at pi seconds, I hit it with the bat. Now it'll start to move. We go through this example, find zeta, find omega n. We learn it's underdamped. We can do the Laplace transform of both sides. You look at the table, there is a Laplace transform for a shifted Dirac delta. That ends up being e to the negative pi s. This should be x of s. Emery, add that to your sheet of my errors. That should be x of s. Thank you. So we'll do this on Thursday, this type of problem. There's one on the practice exam that's kind of similar to this inverse Laplace. But generally, you'll look at the table to find something that fits it, take the inverse, and you can find what x of t is. We did this example in class. I recommend doing this on your own as practice, but you'll get the thing that you want out of your response. Any questions about this concept? Questions? Now, it's how bad are we right now? How sleepy are we? 5 out of 10 or 100? Okay, that's good. Hold on. Yes. It depends. You would have to know what the fundamental is. I told you that this happens to be the fundamental. It doesn't have to be 1 the fundamental. It could be 16. It doesn't matter. Then you're looking at multiples of that fundamental. So if the fundamental was 16, the next frequency would be 32, 48, 64, something else after that. See what I'm saying? So it's multiples of that fundamental, which you have to find on your own by looking at the graph, or I give you the period, you have to find out what it is. That make sense? Cool. So we have 6 minutes left of class. We are done with this note set. I don't think we're going to get through anything with note set 14. So what I'm going to say is that we will do note set 14 on Thursday, followed by the practice exam. Then I'll do my PowerPoints, and then that'll be the last day of class before the final on Friday. Yes. I'm going to record on Thursday as well. I'm going to upload this to YouTube when I get back to my office. You can go look at that online. If you have questions, please come talk to me. Thanks for your attention. I know it was a long class, but we're almost done. Bye, guys.